Hello, this is Calculus Early Transcendentals, studying from James Stewart's calculus book, and we are discussing the techniques of differentiation, and this is section 3.2, the product and quotient rules. Okay, so let's be clear. We're going to come up with two different rules for the derivative of a product and the derivative of a quotient, and we want to be clear that the derivative of a product is not the product of the derivatives. You must use the product rule. And the derivative of a quotient is not the quotient of the derivatives. And let's also be clear that every single one of our derivative rules comes directly from the limit definition of the derivative, which is that limit of the slopes, or the limit of the difference quotient. So you see here before us the product rule, and again, we're starting from that limit definition. So if y is equal to f times g, then the derivative of f times g is going to be the limit as h goes to 0 of f of x plus h times g of x plus h minus f of x times g of x. And this is an interesting, neat proof that requires some innovative algebraic manipulations. So in this very second step, we are just adding and subtracting the same values. That is f of x plus h times g of x, and then we're also subtracting that f of x plus h times g of x. And then in the very next step, we're just rearranging the terms, and we're allowed to rearrange terms as long as we continue to add what we're adding and subtract what we're subtracting. And so we're just moving this item here to here, right? And so in our very next step, we begin, and then we also swap spots, I believe, the f of x plus h. Yes, we're also moving this one here. And we're also moving that over here. Good. All right, and then in the very next step, we actually factor out common factors from those four terms. So in the first two terms, we're factoring out the f of x plus h because we see it as a factor here, and we also see it as a factor here. And we end up with g of x plus h minus g of x. And over on the next two steps, we see that we've got g of x is the common factor, and so we factor out that g of x, right? And we have one big, huge fraction there that is a sum, and the very next step, we just split up that sum into different fractions with the same denominator. And then we use our limit laws. The limit of a sum is the sum of the limits, and so we're still adding those things. And then once we take that limit, we're looking at the limit of a product, and that's going to be the product of the limits. And the variable in that operation of taking the limit is h, and so h is the one that is going to 0. G of x, for example, in this item, the limit as h goes to 0 of g of x is just g of x because the limit of a constant is a constant. And if we plug in h everywhere, again, we also see that we've got in our very next step the limit as h goes to 0 of g of x plus h minus g of x over h. That does become the derivative g prime of x, and the limit as h goes to 0 of f of x plus h minus f of x is the derivative f prime of x, and the other two are constants, so in that limit operation. So we now have, directly using the limit definition of the derivative, f of x times g of x is going to be this rule. Okay, so notice that I actually tend to swap spots, and I will say that the if y is equal to f times g, then y prime is going to be the derivative of the first times the second plus the first times the derivative of the second. Okay, so this is going to be very helpful when we go and observe that we've got a function that is the product of an algebraic function and a transcendental one. Okay, so let's take a look at this example. G of t is equal to t squared plus 1 times e to the t. And so I see a product right here. Okay, and I see my f times g. And so my g prime is going to be the derivative of the first times the second plus the first times the derivative of the second. And sometimes I like to advise students who are first practicing this to maybe build a small table and then make those substitutions into that table. So for example, here f equal to t squared plus 1. What is f prime? That's 2t. And g equal to e to the t, g prime is also e to the t. So now when I go to plug in my product formula, I can plug in those values. And my f prime is 2t, my g is e to the t, my f is t squared plus 1, and my g prime of t is e to the t. Now in this case, I see two terms and they both have a common factor of e to the t, so I can factor that out. And I would get 2t plus t squared plus 1. Good, and that is my g prime of t. This example asks for a second derivative, so if I go for the second derivative, I do see another product again, and I have my f times my g, and so my g double prime is going to be the derivative of the first times the second plus the first times the derivative of the second, and I can make my chart again. If f is equal to e to the t, then f prime is e to the t. If g is equal to, and I'm just going to rearrange the terms to be descending powers, t squared plus 2t plus 1, then g prime is going to be 2t plus 2, right? Plus 0, but we don't need that 0. So in building my skeleton at first, I'm going to say that this is, I just want to make spaces knowing that I'm going to multiply. And the derivative of the first is e to the t times the second, and the second is t squared plus 2t plus 1 plus the first. The first is e to the t, and the derivative of the second, and the derivative of the second is 2t plus 2. Again, I see a common factor of e to the t, so I can factor that out. And I'm left with t squared plus 2t plus 1, and then plus a 2t plus 2, and I can simplify that by collecting like terms, and I end up with t squared plus 4t plus 3. Good. And then it says determine all points where G has a horizontal tangent. When does G have a horizontal tangent? Horizontal tangents have slope 0. And if we remember that our first derivative gives us a function that will be able to determine the instant rate of change or the slope of the tangent line at any point. So we want to say find t where the slope is equal to 0. So in other words, where g of t is equal to 0. Good. And we have from above that our g of t is equal to, or g prime of t from above is e to the t times t squared plus 2t plus 1. And when does that equal 0? When we have the 0 factor property. If a times b is equal to 0, then a is 0 or b is 0. So this will happen when e to the t is equal to 0, or when t squared plus 2t plus 1 is equal to 0. The e to the t is an exponential function. This happens never. So that's never equal to 0, so we won't find a solution on that side. But on the right side, we've got a quadratic equation, and I can do the factor property or the quadratic formula. You take your pick. I see that this is t plus 1 times t plus 1 equal to 0. And again, that will tell me that will equal 0 if t plus 1 is equal to 0 or t plus 1 is equal to 0. And that's the same equation, or when t is equal to minus 1. Good. All right. Now the quotient rule can be derived either using the chain rule or another limit definition, and is a bit more involved. So in the interest of time, I'm just going to present to you the quotient rule. So here is if we've got the derivative of a quotient, and we can't manipulate it so that we can use the product rule, then we're forced to use this quotient rule. And I tend to like to use Newton's prime notation to help students see the formula. This is also a decent tool to remember, because we are seeing that if y is equal to f over g, then y prime is going to be the derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. Now, in the little tool or mnemonic device that they have here, they just swap spots from what I was saying, right? G times f prime is the same as f prime times g, but in that order, you can use this. The derivative of a quotient is the product of the low times the derivative of the high minus the high times the derivative of the low over the low squared, right? And you can say low d high minus high d low over low squared is pretty decent thing that many students use to memorize. All right, so look at this example. We're not ready for the chain rule yet. That comes in a couple sections. We would otherwise be able to use the product rule with the chain rule to calculate this derivative, but we can use, now that we have the quotient rule, we can use the exponent rules to turn it into a quotient. So we have that x e to the minus x is the same as x over e to the x, and there's my f over g. So again, if you want to use a table, we can say our top is equal to x, and our derivative of x is 1. Our bottom is equal to e to the x, and our g prime is also going to be e to the x. And so now our y prime here is going to be the derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. And now I'm going to plug in my values. And so the f prime is 1, g is e to the x minus x times the derivative of e to the x, which is e to the x, all over e to the x squared. I can factor out. You do want to try to simplify if you're trying to find a function for the derivative. Otherwise, if you are within a problem that's just asking for a specific value of the derivative, I would not bother to simplify, and I would just evaluate the derivative at that particular moment. But here we can simplify, and we've got 1 minus x over e to the x squared, and I can cancel 1 e to the x with 2 of them to leave 1 to e to the x left over, and I finally get that we've got 1 minus x over e to the x is our derivative. Okay. All right. How would we do this equation? So this is an example of we only need to find one derivative or one slope. We don't necessarily need to have a simplified derivative expression in order to evaluate at a particular point. So here it's asking, find an equation of the line tangent to the curve of f of x equal to 20 square root of x over x squared plus 4 when x is equal to 4. Okay, so our first step is find, we can find our point. When x is equal to 4, then f of 4 is going to equal 20 times the square root of 4 over 4 squared plus 4, and that's going to be 20 times 2, which is 40, over 16 plus 4, which is 20, and we're going to get 40 divided by 20 is 2. So our point for our equation of the tangent is going to be x1, y1 equal to 4, 2. Good? So that's our first step, is what's our point? What's our second? Find the slope. So we want to find the slope of f of x at x equal to 4. So we will be evaluating f prime of 4. And we don't have to use the limit definition. We can now take the derivative using the quotient rule and then evaluate it at x equal to 4. So here we go. If y here is equal to 20, and I'm going to change it now to x to the 1/2 over x squared plus 4. And there's my quotient, and I'm just going to say my y prime is going to be the derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. I'm saying that a lot to get you guys to memorize. And then I'm going to plug those values in. So the derivative of the top there is going to be 1/2 times 20, which is 10, x to the minus 1/2. That's the derivative of the top times the bottom. And the bottom is x squared plus 4 minus the top, which is 20 times x to the 1/2 times the derivative of the bottom. And the derivative of the bottom is 2x, not plus 4, all over the bottom squared. And the bottom squared is going to be x squared plus 4 squared. Resist simplifying that, and resist distributing the exponent. That does not equal x to the 4th plus 16. Okay, so now that's my derivative. Yes, it doesn't look all that great, but I'm going to plug in my values. Now I might want to remember that x to the minus 1/2 here is 1 over the square root of x. Good. So now what's y prime? Evaluated at 4, and this is going to give me my slope of f of x at x equal to 4. And I'm just going to plug in my values then. So I'm going to say that this is 10 times 1 over the square root of 4 times 4 squared plus 4 minus 20 times the square root of 4 times 2 times 4 all over 4 squared plus 4 squared. And so all I did was evaluate where my x's were, right? And I'm just plugging in my value of 4. Now I get to simplify. 10 divided by 10 divided by 2 is going to give me 5. And we've got 4 squared plus 4 is going to give me 20. Minus 20 times 2 is going to give me 40. And we've got times 8 here. And that's going to be all over 20 squared. Good. And you can multiply, or you can factor out. Sometimes I like to factor out at this point. I'm going to factor out a 20, and that's going to give me 5 minus 160, because that's 20 times 8, right? No, 32, right? If I factor out a 20 from 40, 40 divided by 20 is 2, so it's going to be 16 over 20 squared. And now I can cancel my 20s, and I'm going to get 5 minus 16 is negative 11 over 20. Good, and that is my slope. So how do I put together my equation? My equation of the tangent line is going to be y minus y1 equal to m times x minus x1. We have our x1, y1 is our 0.42. We have our slope m is 11/20. And all we have to do is plug them in. And so I plug in my y1, which is 2. I plug in my x1, which is 4. And I plug in my slope, which is minus 11 over 20. So that is your equation in point slope form. Of course, you can distribute and simplify, right? So I can say that this is minus 11 over 20 plus 44 over 20, and I can say this is y, and then if I add plus 2, that's going to be plus 40 over 2, or 40 over 20, sorry, and we end up with minus 11/20 x plus 84 over 20, and you can simplify that further if you want to call that 21 over 5, right? But you can keep it in this form. No need to oversimplify. That's nice. All right. So I thought I'd go over just a few more examples of your options and using the quotient rule. So in this case, on the left-hand side, you're still going to have to use the quotient rule to find your derivative, but over on the right-hand side, we actually can rewrite this as y equal to s minus s to the 1/2 times s to the minus 2, just using exponent rules. And you could then distribute the s to the minus 2 by using the distributive property, and we would get s to the minus 1 minus, and we'd have s to the 3/2, or negative 3/2, or minus 1/2. And then in taking our derivative, we could just take it term by term, and this would be minus s to the minus 2, and minus minus would be plus 3/2 times s to the minus 5/2. And you can leave it like that, or you can take it back to a quotient, and you would get minus 1 over s squared plus 3 over 2 times s to the 5/2, and that's 2.5, right? So I would want to multiply on the top and bottom of the first term. If I wanted to put it back into a fraction, I'd want to multiply by 2 times s to the 1/2 over 2 times s to the 1/2, and multiplying by 1 over s squared, and then I'd have the plus 3 over 2 s to the 5/2, and we'd have the same denominator then, and then we could combine the numerators, and multiplying here we would get minus 2 root s plus 3 all over 2 s to the 5/2, or if you wanted to change that to s to the 2.5, so you'd have s squared times the square root of s if you wanted to. Or you can keep it the way that it is, and you can use the quotient rule. Either way, you're going to get the same result. But that is an option when you have a single term. But when you don't have a single term, you must use the quotient rule. And so this would be f over g, and our y prime would be the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. So in doing that, our y prime, the derivative of the top, is going to be 2x times the bottom is x cubed minus 1 minus the top, and make sure you minus the entire top, times the derivative of the bottom all over the bottom squared. And that is not x to the 6th minus 1 squared. Okay. And you'll want to clean things up and collect like terms here, and we will get 2x to the 4th minus 2x, and then this is going to be take away 3x to the 4th and take away 3x squared, and you'll want to clean those things up and put in descending powers. 2x to the 4th minus 3x to the 4th is minus x to the 4th minus 3x squared, and then minus 2x all over the bottom squared. And if you wanted to factor out that x, you can, but you don't have to. Okay, hopefully this clears things up. One final one. let's say we wanted to take, if we had y equal to x squared sine x, find y prime. Y prime, that's going to be an f times a g, so y prime is going to be the derivative of the first times the second plus the first times the derivative of the second. And this is my f and this is my g, so the derivative of the first is 2x, the second is sine x, plus the first, and the first is x squared, and the derivative of the second is cosine x. If I wanted to take the second derivative, these would be both product rules, right? So I would still have to do a product rule here. And so I still would have the derivative of the first times the second plus the first times the derivative of the second. And that's going to give me the derivative of the first is 2. The second is sine x plus the first is 2x. And the derivative of the second is cosine. And then I would also, on this side, still have to plus, and I'm still going to get the product rule here as well. And so this would be the derivative of the first times the second plus the first times the derivative of the second, where this would be my f and this would be my g. And so the derivative of the first there is 2x, and then we'd have times the second plus the first times the derivative of the second, and the derivative of cosine is minus sine. And then I'd want to look for common like terms, and I do see that I've got one here and I have one here. So we can say this is 2 sine x plus 4x cosine x, and then minus x squared sine x. And there's our double prime. Okay, pretty good. Hopefully this clears things up. So if you spot products, you have to use the product rule if you're asked to find the derivative. If you spot quotients, if it's the denominator is a single term, you do have options to go bring it upstairs, clear parentheses, or even use the distributive or use the product rule. But when you have more than one term in the denominator and you can't cancel out the denominator, you're forced to use the quotient rule. Okay, I'm going to stop here and I'll see you next time.